Awesome. It looks like we are live. Yep. So hello again. Welcome in the second event of Dotnetos Week. So basically, Dotnetos Week is our online event that we come up with that is focused on .NET. But again, we are trying to do it from a few different perspectives. So hopefully during this session with Marcin today, you will learn a lot about security and also quite interesting things related to regular expressions. So yeah, today we are hosting Marcin Hoppe. I worked with Marcin a few years back, and I must admit that I'm still amazed by his capability of combining so many different aspects of engineering in one person. Especially when it comes to both security and stuff related to different frameworks, different languages, and different approaches to software engineering. So yeah, just let me go through a few slides. So as I mentioned, that's the Dotnetos Week, our online event. We are doing it with the help of our partners. So that's the KMD Poland and Demand Technology Center that they help us with a few aspects of providing this online event. I wanted to just briefly mention and go through the plan. So yesterday we hosted Maoni Stevens. She was discussing various aspects related to pinning. Today we are hosting Marcin Hoppe. Tomorrow we will have .NET discussion panel, a few interesting people discussing various aspects of, again, .NET 5 and like the whole family of our lovely framework. Thursday, Sebastian Solnica will discuss something related to debugging, tracing, and really low level. And the last but not least, the last person during the whole Dotnetos Week this year, we will host Stephen Taub, and he will discuss all the improvements that you can observe in .NET 5. And I wanted to strongly encourage you to just click this magic subscribe button wherever there is this beautiful red button, subscribe and enjoy watching the session. So yeah, without further delay, let's welcome our guest and let me switch the slide deck right now.
Okay, thank you. Thanks for having me. As Shimon mentioned, my name is Marcin Hoppe, and for the majority of my professional career, I was a .NET developer, or at least working on systems that had a significant .NET component to them. And in the last couple of years, I actually became a security engineer. And this aspect of was like which elements of our day-to-day development can become an attack vector is something I'm super passionate about. And today I'm gonna talk about a very specific type of attack that has all to do with performance and resource consumption. And I'm gonna tell you how .NET 5 helps you hopefully prevent those attacks from happening. So as far as the agenda goes, I will start with a very brief refresh of regular expressions in .NET. Then we will move on to one particular type of denial of service attack that comes from misuse of regular expressions that is called regular expression denial of service, or ReDoS for short. Then I will share a few techniques on how to fix and protect against ReDoS attacks. And then we'll also take a look at what .NET 5 can do for us in with the goal of mitigating those attacks in the first place, so that we don't have to worry about them in the first place. So what are regular expressions? So you might know an old joke that if you have a text processing problem and you apply regular expressions to solve it, now you have two problems. There is some truth to that, but the simplest way to think about the regular expressions is that this is a specialized domain-specific language for text processing. What it boils down to is that it allows us to define patterns that we look for in text, in strings, documents, and things of that nature. It is very flexible. It's not NP complete, but it allows us to define very complex patterns to look for within text in a very flexible and concise format. So it allows us to write reusable code that processes text and just use different types of regular expressions depending on what we are looking for. In many cases, regular expressions are going to be extremely fast. As we're going to take a peek under the hood a little bit, and I'll tell you a few things about how regular expressions work under the hood. So you're going to see where this performance boost comes from, and why it might be a lot faster than handcrafted code. What regular expressions allow us to do is to implement multiple different use cases in text processing. So we might use them to implement searching and finding specific patterns in text data. We can use it to edit data, to replace patterns with different values, or even parts of the same pattern, to delete data. I think removing white spaces is probably something that comes to mind first, but we can make it a lot more complex and useful than that. And we can also use regular expressions to split a very long and complex string into smaller pieces based on patterns of those separators. Yep. So how do we construct regular expression patterns? So there are a couple of different constructs that go into a regular expression pattern. What I'm showing you here is just the tip of the iceberg, and a few things that are very common and quite simple. Also, what I'm showing here, and we'll talk about all those things in a little while, are all you need to understand regular expression denial of service attacks and all the other expressions that I'm gonna show later on. So let me take you on a really quick tour of all basic syntax elements of regular expressions. So the first one, and probably the most common, are different character classes. So whenever we use a character class in a regular expression, it matches one character of a particular type. So we may start by listing specific characters inside the square brackets. So this is this first pattern. It would match letters A, B, and C, or digits from 0 to 9. So this is something that kind of matches a set of explicitly provided characters. Then /W is something that is a character class that matches alphanumeric characters. And /S matches different types of white space, so a space, a tab, and so on and so forth. /D matches digits. And interestingly, a dot matches any character that is not a new line. So we're going to see how those things are useful in a few examples later on. You probably notice that some of those some of the characters that we usually encode and escape in languages in the C family, such as the new line and the tab, we do the same thing in regular expressions. So /n stands for a new line, /t stands for a tab. And what I mentioned before, that dot encodes any character. If you want to encode like dot itself, we need to escape it as well. So /dot means the character dot. Anchors are elements of a regular expression pattern that place it at a specific position in the string, right? So the dash here means the beginning of the string, and the $sign means the end of the string. That's a little bit simplified. It's a bit more complex in that when we have multi-line string, they really mean the beginning of the line and not the entire string. But for the purpose of this presentation, The first one is just the beginning of the string. The other one is the end of the string. We can also look for like specific, not only matching single characters, but groups of characters defined by a pattern. Whenever we want to map a group of characters, we enclose them in brackets. And the first example matches a string that's either netcore app0 or netcore app1, netcore app2, up to netcore app3. So those patterns within brackets can be either a stream of characters, a set of characters, or a character class. Like this square bracket 0 to 3 is a character class. And with many patterns, we can also deal with things like optionality and repetition. So we have elements that are called quantifiers. So one of the basic quantifiers are asterisk, and this means 0 or more occurrences of whatever comes before that quantifier, and we will see that later on. The question mark means optionality. So whenever we have something followed by a question mark, it means that we want to match when this something is there, or it might be missing. And the plus is means one or more occurrences of whatever stands before that plus sign. Those are very flexible, but sometimes we need to be more specific. So whenever we want to say we want to match this thing, like it happens 3 times, one after the other, we may use this syntax with curly brackets. And if we want to say that we want to match this particular character or a character class occurring between 3 and 7 times, we can use the curly brackets with 2 numbers separated by a comma. There are probably many more. As I said, regular expressions are super complex and very powerful, but those are the things we're going to need. The last syntax element that's going to be useful for us is alternation. So whenever we want to say match this or the other thing, we might use the vertical bar character, and we list the options separated by those characters. That was a whole lot. So maybe let's take a look at an example of a very simplistic regular expression that matches an IP address. We will see that expression later on in action, but if you see at that pattern in this first line, it says dash, which means the beginning of the string, then followed by /d, is, you remember, it's a digit, and then we have the quantifier, which says that after the beginning of the string, we're looking for a digit that occurs between 1 and 3 times. So if you look at the IP address below, what you see is that the beginning of the string marked as this thick black dot matches the first character in the pattern, then 192 matches that other segment. All right, so it matches between 1 and 3 digits. Here we have 3 digits. And then the next element in the pattern is actually a dot. You see the backslash there is used to escape it, and the dot after the 192, this is what matches. And now you see that all those other IP address segments are repeated. So we have 168 matches another segment, then a dot, and then we have a 0. Which also is a single digit, not 3, but it still matches that that precondition, that condition that it's between 1 and 3 digits. Then we have a dot, and then we have our last segment, and then we have that thick dot that matches the $sign, which is the which denotes the end of the string, and this allows us to take an arbitrary string and validate if it's a valid IP address. And we can take it from here and do many different things with it, like split it to its constituent parts, like all those segments, validate if it's a valid IP address, look for valid IP addresses in a larger string, and so on and so on. So this wouldn't be a .NET week if regular expressions were not a first-class citizen in the .NET ecosystem. So whatever you want to do with regular expressions in .NET, it's hidden in the system.text.regularExpressions namespace. And the most important class that's in there, it's called regex, right? So regex is a class that when you create an instance of it, you need to pass a regular expression pattern to it. Here, it's stored in a variable. You see that the content of that variable is preceded with the @ sign. That's just a little help, so I didn't have to escape all those backslashes inside of the string. So if I wanted to have a /d inside of a regular C# string, I really would have had to use the --//d, and it would make the whole expression a little bit less readable. That's why I went with the @quoted string, where those backslashes are not interpreted as escape sequences. This is fairly common practice when working with regular expressions. And then you see in the next line, I instantiated a regex object. I passed the pattern as the first parameter to the constructor, but that constructor actually can take more than that single parameter, and we can pass a bunch of different options that configure how this regular expression behaves, like different options. For example, if this is a multi-line expressions that consists of more than a single line, and then different elements of that domain-specific language behave slightly differently, and things like is our expression case sensitive, and things of that nature. Here we're passing an option that's actually affecting the performance of it. It's called compiled, and I will explain what that means in just a second. And when we have that regex object, we can actually use it on input data of different kinds to run the matching of the string to that regular expression. Here we're using the simplest form, and we're asking if the string in the input variable matches the pattern described in like stored in the pattern variable and in the regex object. There are more methods on the regex object that do different kinds of things. So isMatch returns a Boolean. So if either the input variable is a match or it isn't. However, if we want to not only know if that condition is true, but we actually want to extract that that matched portion of the string that matches the expression, we need to use the match method. Sometimes what we want to do is to find all places in our input string that match a given regular expression. This is what the matches method is for. And I think by now you can probably guess what the replace and the split methods do. The replace takes a regular expression that's defined by the regex object. It takes an input string and it takes a value that matches should be replaced with, and split returns a collection of portions of the string that are separated by substrings that match that regular expression. I know that if you're uninitiated, that might sound a little complex, so I would recommend going and playing with those methods later on. It's a super useful mechanism. You won't regret that. However, for our purposes here, we will focus on just the simplest forms, the isMatch, and actually extracting that match. So I hope you're wondering what really happens when we instantiate that object the regex class, and we pass it a pattern and a set of options. So the first thing that happens is that the regular expressions engine that .NET has implemented parses the pattern to see if it's even correct regular expression, and then it parses it in a way that's similar to parsing other programming languages. So it creates an abstract syntax tree that describes like all the different operations that or different elements of that pattern that the regular expression describes. And then that parsed tree is actually transformed into a series of opcodes that define what kind of search, find, replace, and split operations actually allow this algorithm or pattern described by a regular expression be carried out, right? So this is probably the most complex part of working with regular expressions internally. It's like, how do we go from that very complex and very cryptic pattern into a set of instructions that actually traverse a string character by character and try to match it. Interestingly enough, this is also where most of the optimizations occur. So our regular expressions kind of define the what of what we want to have, like in a way that is very similar to other declarative programming or query languages. Like, for example, in SQL, you don't really define what the database does, but you define what kind of data you're interested in retrieving from it, and it's up to the database to define how it goes about doing that. And this is very similar. So you provide the what, and the regular expression engine like figures out how to implement that. If the regular expression engine sees any opportunities to apply optimizations, it will likely do it at this stage. So it would analyze different types of patterns, the relationships between each other, and it will use a variety of heuristics to come up with an optimal set of instructions or opcodes to correctly analyze a string. Optionally, those opcodes can immediately be transformed into MSIL, and that is then just in time compiled. And this only happens if we pass that option regex options compiled. If you don't pass it, it will stop at generating the opcodes. And when we invoke one of the ismatch, match, matches, replace, and split operations, it will every time interpret that set of opcodes time and time again. However, if we use the regex compiled options, what the regex engines will do is it will compile that set of opcodes into MSIL. And when we call one of those methods, it will just go and execute that MSIL. So you might think that perhaps we should always use the regex options compiled because it probably generates a much faster code. And that's probably true. However, that element of compiling a set of opcodes into MSIL takes a lot of time too. So there is a trade-off there between the time of the startup, which is building and compiling the regular expression, versus runtime, which is in our case using those ismatch matches and so on methods. So the only advice we can reasonably have here is it depends, and use benchmarks and measure your code. Like a strawman advice, if you're using the regular expression fairly sparingly, then probably using the regex compile doesn't make much sense from a performance perspective. However, if you're using it heavily or on a hot path, then probably compiling it makes more sense. There's also an option if you want to like spit out a separate assembly with the compiled regex. The .NET regular expression engine allows you to do that as well. Although, truth be told, in my practice, I have never used that, but it's an option that's out there. Okay, so far so good, and it sounds really attractive. But it turns out that our regular expressions, even though they normally would probably be faster than handcrafted code, they have a set of kind of conditions where their performance is pretty bad. How bad we're going to see in one of the in one of the next slides, but the behavior I'm talking about is called catastrophic backtracking. So some regular expressions exhibit the behavior where the regex engines kind of analyzes the string from left to right, and it runs into a situation where the match it was trying to make so far was not successful. However, it knows that maybe if it took a different path in one of the earlier characters in the string, the match might have been successful. So it kind of backtracks to one of those previous characters, takes a different route throughout the expression and the different options, and it tries there. If we are unlucky, this might have really, really very bad computational complexity and take a very long time. So what kind of patterns might exhibit that behavior? Nested quantifiers. So if we have, say, 0 or more occurrences of a given character or a character class, and then that is a group that we want to like quantify itself. That is often something that exhibits that behavior, and quantifiers over an alteration is also something that that might be prone to that. There are probably, well, I'm sure there are more of those patterns that are actually subject to active academic research. So there are papers being published and people do their PhDs in regular expression behavior. But based on my practice, more often than not, developers introduce those patterns into the regular expressions unknowingly. So it turns out it's relatively easy to do it just by mistake and not know it. So if you look at this expression that we have here, A asterisk, B, it tries to match a number of A's followed by number of A's, and the string should end, the match should end with a B. It's kind of represented in that little picture here, where you can match the expression going from one block dot to the other block dot through any of the paths here. So you can go through first the upper A, and then you can go through another upper A or the lower A, or you can actually make a loop. And as you see here, there are actually 2 loops that you can make. So the regular expression engine has actually a lot of options to go from one block dot to the other block dot. The match is actually very fast for strings that are a match. So it will try going through one A, then through the second A, then it sees a B, and we have a match. However, if it goes through one A and the other A, and there's no match because the third character is not a B but something else, then it needs to backtrack and take one of the other routes. So after getting to AAA, it looks at the last character, it's a B, it's not an A, so it gets back one character before and takes the other A. It arrives at a B. It's not a match, so it goes back 2 characters and then tries all the other options. So as you see, it backtracks, and the further it backtracks, it actually has the more options to match forward. And if you are really unlucky, like with this expression here, it might have you might be looking at a combinatorial explosion and an exponential growth of the number of paths that the regular expression can actually take. So the problem is usually not with the expressions that are a match or have like drastically different shape. Usually the heuristic is that the worst behavior that we see are those strings that are almost a match, because that means the regular expression engine has like a lot of successful paths to take, and that means it will have more opportunities then to backtrack and use those use those once again. So if you're thinking about like, how do I test for this, and what kind of strings do I supply to my regex to test it? Think about things that are almost a match. So they have huge parts that are actually correct, but for example, don't match at the end of an alteration or a quantifier. Then you have a fairly high chance of finding one of those. Like if you like data and numbers like myself, it's actually a very good idea to try to quantify what that means. How much slower does it get? And believe me, it can get very slow. So what I have here is a simple benchmark.net benchmark. The regular expression stored in the backtracking regex variable is just to like demonstrate an effect, is a very degenerate case of the pattern that we have seen in the previous slide. So those are 7 loops that can backtrack and followed by a B. And then we have a set of input variables that you can see are almost a match. None of them actually matches this pattern because none of them has a B at the very end, but they have tons of A's, and that is a lot of opportunities for the regular expression engine to actually backtrack to one of the previous E's and take all the other available patterns. And this is exactly what the .NET regular expression engine will do. It will take all of those available paths throughout this looping graph that we have seen here, and it will analyze all of them to potentially find a match. So I ran this benchmark on .NET Core 3.1. As with any benchmarks, be careful, run them a couple of times, and definitely run them in release mode. Notice that what I'm doing here is I'm using the match method, and I'm actually returning that result from the method. This is to eliminate the effect of known as dead code elimination. So compilers are very smart. So if I just called regex and did nothing with the result, there's a possibility that the compiler would optimize that away as an operation that doesn't have any side effects. So in order to counter that, I'm actually doing something with the return value and returning it from the benchmark method. So I'm using benchmark.net, and it's a pretty handy benchmarking tool for .NET. It spits out a hell lot of information. So I stripped it down for you a little bit. What you can see here is that we are running our benchmark on .NET Core 3.1. This is kind of important because later on we will run exactly same benchmark on .NET 5, and we're going to see what the difference is. But you can see that we have all those different input variables that we have specified here and here and here and here, and they are listed here. And then we have the mean time of execution for all of those regular expression matches. I would encourage you not only to look at the progression of those numbers and how they are, it's not scaling linearly. Like you can see that, for example, this string here is twice as long as this one here, but the relationship between those two numbers is definitely not linear. It's not twice as long, it's many times longer. And this one here has 21 characters, and the next one here has 42 characters. And you can see that the discrepancy here between the processing time is actually several orders of magnitude. So that is definitely something that smells like a combinatorial explosion. One thing that I would also like you to remember here is the unit here. We're talking microseconds for evaluating a match for such a simple string, and we're talking like over almost 120 microseconds, and for string of 42 characters, we're talking like over 4 seconds. Like that is a lot. So if we can, you can only imagine what would happen if I passed a string of 100 A's, right? It would be, I'm not entirely sure when this would be done. I had some slides to prepare for you here, so I didn't really want to do that. But if you want, then I definitely recommend you you do that. So you might ask, okay, so what does it have to do with security, really? That sounds like a performance problem. So more often than not, things that can easily consume a lot of our resources can very easily turn into a security problem. And there are two companies that were not subject to attack because they managed to knock themselves out by having those kind of behaviors in their regular expressions. So in 21, one of the largest CDN or content delivery network providers in the world, Cloudflare, deployed a web application firewall rule that exhibited this behavior. So what they noticed is that the processes that they had that were evaluating those rules on all the incoming requests that were using those rules just spike initially to 100% CPU usage and caused a global outage. And believe me, like Cloudflare has global infrastructure, and it's a very resilient service, and it actually went down for a good number of reasons. There is a very good postmortem available online for this particular incident, and a lot of that postmortem focuses on that exponential behavior of the regular expression that caused this. A similar thing happened to Stack Overflow in 2016. So they had a regular expression that they didn't know have this flaw, and someone posted a slightly malformed post that ended up on the front page. Unfortunately, that malformed post and that regular expression caused the CPU usage to spike and prolonged the response times significantly. Unfortunately, at that time, Stack Overflow's health check mechanism was using the homepage. So the load balancer probe that was looking if a server is alive was actually pinging the homepage. So when they saw timeouts caused that by high CPU usage, it started to take those servers out of operation. Unfortunately, it was a bug in the code, and this post was on the homepage. So each and every server was like taken out of service one by one, causing a global Stack Overflow outage. And this kind of regular expression, you can see that it affects even some of the largest websites. But if you have a system that relies on an event loop where you have a single thread that's accepting incoming requests and hands them off to processing somewhere else, in terms of all the outgoing I/O operations to like databases and other backend microservices and stuff, like this kind of vulnerability can kill those systems right away. Like the most prominent system, one of the most prominent technologies that exhibits this behavior is Node.js, which is a JavaScript server-side of execution environment, which by design is single-threaded. So if there is a regular expression denial of service bug in Node.js code, that is usually very serious because there's a high chance it's easily exploitable into a denial of service situation. And you might still think that, yeah, that's like maybe kind of a problem, but in the world of like auto scaling and things of that nature, like we just throw more cloud resources at the problem. So unfortunately, if you don't configure order scaling properly, you might not be looking at the denial of service, but you might be looking at denial of wallet. So a denial of wallet is a kind of attack where the resource being exhausted is not storage, it's not CPU time, it's not your memory, it's actually your cloud bill goes out of hand. So like defense in depth, if you want to protect, you're running, for example, a third-party application, you don't know what kind of denial of service attacks it's prone to. Remember to set limits and alerts on your cloud spend. I think every sane cloud provider has this ability. So before you deploy anything, make sure you will not go out of business. And if you're using a personal credit card to host your little blog application, do that too. You will thank me later. Not only if you have like an actual attacker, but then maybe if just things go south in and of themselves, like for Cloudflare and Stack Overflow. Okay, so how do we get rid of those types of vulnerabilities in our code? So my advice number one, don't take regular expressions from strangers and don't evaluate them within your application. I know there are a bunch of scenarios where you might want to let users kind of define data validation rules and things like that, and it's very tempting to allow them to specify their own regular expressions. However, if you do that, they may insert a regular expression that exhibits this ReDoS behavior and then hit your application with a malicious payload and then take your application down. That is entirely possible if you are accepting and evaluating untrusted regular expressions. Then, assuming you're not doing that and you're kind of worried about your own regular expressions, then unfortunately you will have to audit them in some way and analyze them if they exhibit that behavior. Unfortunately, this is kind of hard even for people who are experienced regular expression users. So as you've seen, even expressions that look relatively simple and relatively benign can cause like, significant performance problems. And this is a hard-won lesson, and like I always advise to learn on other people's mistakes. Do not generate regular expressions in runtime, for example, to generate data validation rules for your data, depending on what that data is. This is something where I have inadvertently in the past generated ReDoS vulnerable expressions. So maybe learn a lesson here. Don't do that. So what do we do if like finding those patterns is hard? As I said, there are people doing actual PhDs and publishing papers about those things, and many static analysis security testing tools, or SAST, have some rules that will catch some of those. It's definitely worth deploying those tools and analyzing your regular expression patterns for those types of vulnerabilities. So there are SAST engines that are like general and support a number of different programming languages, including C#. But there are tools that focus on regular expression analysis itself. So this will require a little bit of work from you to extract your regular expressions that you're using from your source code and using those tools to identify potentially vulnerable regular expressions. And last but not least, it's quite hard. If you're using regular expressions, truth be told, it's quite hard to avoid this completely. So apply defense in depth and plan for what do you do if a vulnerable expression actually like finds its way to your source code. And the best way to do that is to actually do damage control and make sure that even if you observe this runaway behavior, you have some limits in place that will terminate a request or shut down the process if it goes south and spends an enormous amount of time evaluating that expression. Fortunately, .NET allows you to do that fairly easily, and we will look at that in just a second. So let's assume that we have identified such a vulnerability. Like, what do we do with that? How do we fix it? If you can, probably replacing that regular expression with just a hand-coded algorithm is something that I would recommend, because then you have full control over how you do that. And you can make sure that the new expression is actually or the new code actually doesn't exhibit that same behavior, that same or other behavior, right? So you might use string methods such as starts with or ends with or index of and last index of and split. For complex expressions, it's actually a very, very complex task, but it might be your only option. If you're adventurous, you might actually go and try to fix the pattern itself to eliminate those parts of the pattern that cause that backtracking. It requires a deeper analysis of the pattern itself. But if, for example, you're working with a library that does input validation and all it does accept are regular expressions, and you can't really easily replace it with handwritten code, that might be your only option. So the general high-level algorithm here would be just to find the ambiguity that allows the regex engine to backtrack and try to figure out a pattern that is functionally equivalent that does not exhibit that behavior. That's the art here. What you can sometimes do is to split one regular expression that tries to be overly clever, and by that cleverness, it includes those ambiguous patterns, and split it into not just one expression, but maybe like a series of smaller expressions that you can use to analyze your string. And here we have two very simple examples of like how do you eliminate that ambiguity. First, we have a pattern that tries to be a very general way of matching an email, which is essentially something at something else. It turns out that even this simple pattern can exhibit catastrophic backtracking. But if we kind of replace the first dot with basically the dash here in the character class says everything other than at, it turns out that this simple change removes that behavior, and that pattern becomes much easier for the regex engine to analyze, and then it can linearly just traverse through the string and try to match it. The similar story for the lower expression, which is a set of digits followed by a dot and potentially followed by a dot, because you see that that dot is followed by a question mark, which means it's optional, and potentially followed by a set of other digits. The problem here is that this dot is optional, and if you're trying to match something, the engine may backtrack into the /d plus that is before the dot if it doesn't find the match after the dot. The second pattern here is functionally equivalent, but doesn't have that problem. If you like control the design of your application, you might achieve additional protection if you validate the data you're passing to the regular expression engine before you actually do that, right? So first, make sure you're passing the data you're thinking you're passing into that regular expression. So some regular expressions might be designed with the idea of only working with trusted data. So for example, we have some regular expressions that help us verify the correctness of a configuration file that is being supplied by your system administrator or some other tools, and is not very easy for attackers to get it into your system, right? And in those cases, you can be much more relaxed with your regular expressions. However, in the day and age of code reuse, if you take that regular expression and apply it to data that are coming from outside of your system that you don't necessarily control, and that might be controlled by the attacker, that same expression that you just didn't test for ReDoS might exhibit that behavior, and it might open up an attack vector. And it's also worth taking a look at the size of your data, because if you're looking at very short strings, then probably there are not many regular expressions that will cause a significant problem. And if you know that your input data in a particular, I don't know, a form field or an HTTP header or whatnot are supposed to be relatively short, be sure to check that before you invoke the regular expression engine. I've seen code where the input data is first passed to a regular expression engine, and then the length is verified later on as an additional rule. Don't do that. Do it the other way around. If the data is too long for the format that you know should be correct, don't pass this data to regular expression later on, because that, if your regular expression has a ReDoS vulnerability, then it's cheaper to discard this data upfront, and checking length is usually much cheaper than evaluating regular expressions. If none of those things, none of those things that I just described are always possible to do, or are 100% sure way of getting out the ReDoS, we might have to think in terms of defense in depth, which is planning for our previous defenses to fail. And for regular expressions specifically, authors of .NET kind of saw that and baked it into the API. So you see that here it's a very similar code to what we've seen before, but this time around we pass an additional time span parameter to the regex constructor. And if the regular expression evaluation kind of runs away and exceeds that timeout, the engine will throw the regex match timeout exception, and then you can decide what to do with it. More often than not, that means that the data isn't valid, and you can just discard it. But at a minimum, you are able to control the CPU consumption and your request processing time, so you will not get timeouts. Interestingly enough, this seems like a fairly obvious thing to do, but there are very few regular expression APIs that have this baked in. So it's very cool. It's very cool that .NET has this. Interestingly enough, this is also used within the .NET framework and ASP.NET Core itself internally. So regular expressions are used quite a bit within ASP.NET Core, and whenever there is this usage of regular expressions, .NET internally always uses a timeout, which is a good thing to know. Last but not least, I run exact same benchmark on the exact same computer. You can compare, like, everything is the same, except for the version of the .NET Core runtime. So I ran this on .NET 5 on my Mac. Nothing has changed, and what you can see here is an interesting relationship in that this mean processing time is really increasing linearly. So we don't see this combinatorial explosion anymore, and it's much better. It's much more stable. And if you were listening carefully, I asked you to also look at the unit. There we have microseconds, but here we actually have nanoseconds. So it's not only much more stable in time in terms of times of execution for this particular expression, it's also much faster. Actually, the regular expression engine received a lot of love and care for .NET 5, and it has multiple different performance improvements that contribute to this number. But there is one particular improvement that is especially helpful for preventing ReDoS attacks. And I told you about groups. Those are things that we kind of want the regular expression engine to match as a whole, so that we could either extract it or use in a replacement or things like that. And the pattern here is that we surround those with brackets, and then put a pattern inside of this bracket. The regular expression language has a concept known as atomic groups. So those are groups where essentially we say, if you match this group, regardless of what happens afterwards, do not backtrack into this group. So it's essentially like it disables backtracking for a part of a regular expression. It's by no means new. It has existed in .NET before. It's also not something that is specific to .NET. Other regular expression implementations kind of have this too. It can be known by other names like non-backtracking sub-expressions or atomic sub-expressions or once-only sub-expressions, because like we want the regular expression engine to only match it once. So let's look at a simple example of how it works. So we have a simple pattern that's A asterisk B, which matches a stream of A's followed by a B. And let's take a look at what happens when we have that almost matching string that's AAA. So first, the engine kind of goes through the entire string. It gets to the end of it. There is no B at the end, so it's not a match. So what it does, it backtracks 1A and starts again. It doesn't find a match. It backtracks even more, and then tries to follow all the paths throughout that loopy graph that you've seen before. And if it exhausts all the paths, it says there is no match. So if this string was longer, there would be a lot of backtracking there. However, if we enclose this A asterisk in an atomic group, what it will do is it will match those three A's, and it will say that after that there is no following B, so there is no match. So in the previous example above, the engine was actually starting to backtrack, but here it sees that all those three A's are an atomic group, and the engine cannot backtrack through it. So it will immediately determine there is no match, and it will return the result accordingly. So this is a very good protection against ReDoS. However, before .NET 5, you had to know about this, and you would have to use it. You would have to use it explicitly in your regular expressions, which is cool that you can really do that. But the thing about .NET 5 is in this optimization phase that I told you about, where it parses the regular expression into an AST or an abstract syntax tree, it turns this into like a stream of opcodes or instructions that will analyze the string. .NET 5 has a number of heuristics that it can use to analyze your regular expression and insert those atomic groups automatically where they don't change the semantics of your regular expression, which is why we saw this combined with other optimizations explain that terrific improvement that we saw not only in the actual time of processing and execution, but also the stability and the linear progression of the processing time with relation to, or in relation to, the length of the input string. And then again, it's a heuristic. It's not guaranteed to work every time, but for many, many cases, it will be a perfect protection. Or not perfect, but very, very convenient, so that you don't actually have to do much with it. So if there are just 4 things I would love for you to take out of this presentation, is that regular expressions they are very powerful, but they can actually become an attack vector itself. And they may lead to 100% CPU consumption, timeouts, and maybe even affecting your cloud spend. We chatted a bit about backtracking. So I think right now, even if you are not able to locate that in your own expressions, you know that something like this might exist. So you might read up on it and try to experiment with your regular expressions. And the tip here is, if you have alternations and quantifiers, try to test your expression with the data that almost matches. So it matches parts of your expression, but not entirely. And if you're dealing with untrusted input data, so things coming through, microservice calls, HTTP requests, and things like that, always use timeouts. Like that may save you if you have a bug you don't know about, or there is a ReDoS vulnerability in a third-party library that you're using, and so on and so on. And if you absolutely have to accept regular expressions from your users that cannot be fully trusted, then there is no other way around it. You have to use timeouts to make sure those expressions don't blow up your application. And if you can, plan migration to .NET 5, because you should be much better protected against regular expressions out of the box. I hope you enjoyed it. That's all I had for you today. And then again, I'm super happy that I had the opportunity to share all of this with you today. Thank you.
Awesome. So thank you, Marcin. Before going with all my dead jokes related to security and regex expressions, we prepared something for you. So if that webinar made you interested, please visit this short link, so dotnetos.org/secure, and we've got something for you in there. As I mentioned, if you enjoyed the talk, please go in there and grab that thing. I'm sorry, I need to misquote one person before we go into the proper Q&A. Łukasz Trześniewski, sorry for doing this, but your answer was like answer related to my question. But this reminded me of this meme when there is this dog sitting in the house filled with fire and everything seems fine. And I think that some of the people during this presentation might have had a really bad time and was thinking about the production environments. But it was, at least for me, it was a really interesting talk. We have a few questions, so let me start with this one from Hendrik. You mentioned this tool, that regex testing rules, and Hendrik says that SonarQube has a good set of these.
Yeah, that's entirely possible. Truth be told, I don't have experience running SonarQube on .NET code, but I will take your word for it. One tool that I know works with .NET or C# code specifically, and regular expression denial of service is CodeQL, or like for open source projects, it's called lgtm.com. Looks good to me. It's actually the open source version of the code scanning engine that's integrated into GitHub now. It's called GitHub Code Scanning, and it detects ReDoS, or at least some cases of it, and it supports C# code. As I said, I know SonarQube is super popular with Java, and it probably has good support for regex testing. I just haven't used it myself. I probably will, though, just out of pure interest.
Okay, I think that I'm getting even better in misquoting and misunderstanding, because Henrik said that that wasn't a question. So sorry for bringing that to the table. And let me pick another one. This one from Samuel Martinez, about your favorite tool to create regular expressions.
Oh, that's an interesting question. I know there are a few tools and like debuggers for regular expressions, but like truth be told, I'm a little bit old school, and I like the loopy graphs, and actually I like creating my regular expressions with just pen and paper. That's probably why I don't create very complex ones, but it's a pretty good way of analyzing them. Yeah, but I know those tools. Those tools are out there, and those are like websites that do that, and you have IDE plugins and stuff like that. But I don't have my favorite one.
Okay, I think that was the last one. So again, Marcin, thank you for being with us and for providing all this regex related knowledge. The numbers for .NET 5, I mean, they are really impressive, aren't they?
Oh, they are. They definitely are. If I can recommend something, there is listen to Steven on Friday. He wrote a marvelous article about different types of performance improvements in regular expressions in .NET 5. Not only that, but also like vectorization where possible and other types of performance improvements and micro optimization. So listen to him. I don't know if he's going to cover that in the presentation on Thursday, but if you look for like his blog posts from a few months back, it's definitely, it's a long read, but a very interesting one.
Yeah, I mean, that's the rule, I think, for his write-ups, that they are pretty lengthy, at the same time pretty informative. So yeah, I think that will be ending right now. So again, if you could just show the last slide, Marcin, that if that makes you interested, I encourage you to visit the dotnetos.org/secure. We've got some stuff in there and more is being worked on. And thank you for being with us. And I hope that we'll meet in the next live sessions during the Dotnetos week. So thank you again. Thank you for being with us, Marcin, and see you soon. Take care. Bye.
Yeah, thank you. It was a pleasure. Take care.